do that. Nice. Okay, so still got a few people sort of rolling in. Lovely to see you all. I assume that most of you have been in your assemblies this morning, and then you're coming straight into science, which is exactly what you should be doing. It's fantastic stuff, guys. So we are carrying on with the same timetable that you guys have been using for this at the start of this half term, and now obviously we're carrying that on in these next couple of weeks and seeing how that goes. So I've started you off with this first starter question, which is sort of a recap, because we are going to be going back into chemistry, and we're going to be talking about some of the stuff that we did in last half term, and we are going to really go into the depths of what ionic compounds are today. So looking at the starter slide for me, and I will move on in a moment's time. So I want you to have a little go at this starter question. Which of these conduct electricity, and why do you think that is? So it's a bit of a big thinker at the start here for us. I want you to be thinking about what electricity is, and possibly how these particle diagrams, these structures that you can see here, might allow electricity to flow or not. So I want you to be thinking about that. Which of these conducts electricity and why? Another 30 seconds on that. Let's just check in on you again. I still get a few more coming in. Lovely stuff. Hello to those of you who I haven't said hello to yet. It's lovely seeing such a large bunch of you on a Monday morning after half time. It's great work, guys. Seriously. Pleased, very pleased to see you. Well, not to see you, but to see your names. Okay, so I'm just going to quickly again change my title. Okay, here we go. That's what we're talking about today. And we are still using some of the same vocabulary in terms of protons, neutrons, electrons, bonding. We're going to be talking about how ions are formed again. And we're going to be describing some of the properties of ionic compounds. And so that's what we're going to be doing, focusing mainly on ionic compounds, which allows us to sort of go back over how they're formed. And it allows us then to also talk about what kind of properties they might have, which means what characteristics they have, and how we might describe them. And we're also, towards the end of the session, going to be trying to explain some of the properties of those ionic compounds. So the starter question is still, which of these conduct electricity and why? So we've got this ball and stick diagram here of A. We've got another ball diagram here, which is showing us the structure we're going to be talking about. And there's C, this option here. We've also got a particle diagram, although this is also showing some subatomic particles in here as well. Actually, no, it's not. This is a particle diagram. Then we've got D, another particle diagram, and E, which is showing us some of the subatomic particles. So which of these conducts electricity for my year 9s? Has anyone managed to put an answer in the Q&A? Let's have a quick look if anyone's actually given us a...
They have, sir. We have Chris said image E.
Okay.
As did Sky.
Mm-hmm.
And there are a couple of students said B.
Okay, interesting. Yeah. Miss, that's fantastic. So who... I think you said Sky, did you? Who said that?
Sky and Chris.
Well done, Sky and Chris.
I'll give them an achievement point.
Yeah, absolutely. So E is actually a metallic structure. So we are going to be talking about covalent and metallic bonds, which are the other two types of bonds that you can get in some of our later webinars. Now, we have spoken already about ionic bonds being one of the forms of the ways that atoms can bond together. But if we look at E is a metallic bond, and we can see lots of free electrons there. Those little circles, the pink circles with the negatives in them, they are electrons, the subatomic particles. So because they aren't bonded to anything, they aren't trapped by an atom, they're free to move. So E can conduct electricity. That's really, really good. Fantastic answer there. We could also have identified that C can conduct electricity. Now, those of you who said B for can these conduct electricity, you're right to identify that B has the potential to conduct electricity, because it is an ionic bond. We can see that B is actually an ionic lattice, and we're going to be talking about that in today's session. So B would be able to conduct electricity if it was one of two things. It could either be molten, which means it's been melted, or it could be dissolved, so in a solution. Now, out of all of those pictures that we've got on the starter slides, C is actually a dissolved version of B. So if we look at B, it's got these positive ions and it's got these negative ions. Now, if we were to plop that, like it's a little grain of salt, and put that in some water, it might dissolve, forming C. So C is actually a dissolved version of B. And now, because those ions, the positives and the negatives, are free to move around, they can carry a charge, so they can conduct electricity. So C and E are the two conductive substances there. Bit of a thinker to get your brains in gear on the Monday morning here. So well done to those of you who had a go at that, and well done to those of you who had even tried it, giving a sort of couple of comments in the Q&A boxes there as well. So this is generally the structure of what we're going to be doing today. There's going to be a little bit of sort of student marking that you guys might have to do as well, but I'll explain that as I come through in these slides. And I've given you a few more sort of questions to work through on the slides this week. They're shorter answers, but they do summarize everything that we've done so far. Obviously, again, you're expected to watch the webinar and then to complete the Google Forms as well. But the Google Forms for you Year 9s are usually expected to be set by Wednesday. Okay, so you might want to complete them on that Wednesday session instead. Right, so ionic compounds. It's really important to remind ourselves of what ions are and what an ionic compound is. So as I was saying to you before, just quickly go back up to these pictures that we can see at the very start. There are three types of bonds. So these are three ways in which atoms or elements can bond to each other. And that depends on what type of element they are. So for A, in this first picture, we can see a ball and stick representation, and that might be a covalent bond. So I know that because I've obviously taught lots and lots of bonding in the past, and we are going to go over what covalent bonds are. But they're a form of bond in which atoms, or even elements, are going to be bonded together. So it's a way that they can sort of stay together and form new compounds and things. B is the Ionic lattice. So this is ionic bonds within the structure of B. And we know that because of their charged particles. So we know that because they've formed ions. Now, an ion, as a quick reminder, is basically an atom that has either gained electrons, so it's gained negative electrons to become negative, or it's lost negative electrons to become positive. Okay, and that's all to do with the imbalance of protons and electrons. So we worked out how to show an ion or to draw an ion in the previous sessions. If you can't remember that, go back and watch the webinar because it will really, really help you out. So the final form of bond, just quickly show you, is the metallic bond, which is that E shown on these slides here. So the metallic bond is the type of bond only formed between metals. So it's metal and a metal, and they have free electrons, meaning they can carry a charge, carry an electrical charge. Right, so ionic compounds, really important to remember that ionic compounds, so ions, only form between a metal and a non-metal, these ionic compounds. So the metal has to lose its electrons to become positive. So now it's got this positive charge, and a non-metal needs to gain electrons to become negative. And obviously now if I've got a negative non-metal ion and a positive metal ion, the positives and negatives attract, and it forms an ionic bond. So we can call those forces electrostatic forces, and they're called that because of the electrons, okay, and the fact that they can be rubbed on and off of atoms through static charge. So there's also links between physics in chemistry and biology. All of these subjects in science are really closely linked, and they rely on knowledge about each of the other subjects quite a bit. So it's worth paying attention to all three of the subjects. Okay, now Mrs. created this lovely like cheat sheet. I've named it a cheat sheet because I think that these are really good quick reference points which you can
Love
go
it,
back.
sir.
Say that again, Miss.
I love that you've called it a cheat sheet.
Good. Yeah. Because I quite like. I mean, these are so useful and quick to get back to, and they will just really help you to try and remember the ways that we use the periodic table. So obviously, I've said to you plenty of times before, guys, this periodic table is like an invaluable tool. It's so useful when you're doing your chemistry exams. And that's because you can find out a lot about each of the atoms just by looking at the periodic table. What we're interested in right now is what type of an ion they will form. So at the very start, I've told you that ionic bonds form between metals and non-metals. Okay. And another little key piece of information that you guys should be trying to remember is that metals will always form positive ions. Okay, they will always form a positive ion. Non-metals always form negative ions. So if you're looking at the periodic table and they ask you to work out what the charge of a chlorine ion would be, so that's the chlorine atom turning into an ion. So I already know that chlorine is a non-metal, so I know it's going to be negative. Brilliant. Now, if I then want to figure out what charge of an ion it's going to be, is it going to be a -1 or a -2 or a -3? Then I'm going to use this cheat sheet. And this cheat sheet is basically laying out the simple, easy way you can figure out what charge an ion is going to be. So it's actually easier if I start in group 1. Now, lithium, sodium, all those ones are going to form the +1 ions in the group 1 because they have 1 electron in their outer shell. Now, we know all atoms want to have a stable arrangement of electrons, so they want to have a full outer shell. So for sodium in group 1, it's going to be a lot easier for it to lose that 1 electron to complete its outer shell just inside. Okay, so it's basically got rid of that outer electron and its outer shell to reveal a full shell underneath. So now it's satisfied, it's got a stable arrangement of electrons. And the same would be for any of those elements in group 1. Now, the same sort of idea happens with all of the group 2 elements. They've got 2 electrons in their outer shell, and because they want a full outer shell, they're going to strip off those outer 2 electrons, revealing a full shell underneath. And that is a stable arrangement of electrons. So they're happy again. But because they've lost 2 negative electrons, they're going to have a +2 charge. So we remember that atoms are not charged because they actually have an equal amount of protons and electrons. So say they had 10 protons, 10 electrons would balance that, meaning their overall charge is 0. So when we have an imbalance, if they lose electrons, then they are left over with more protons than they were electrons. So they end up being positive ions. Okay, so the opposite happens for non-metals. Non-metals are actually closer to having a full outer shell by completing it, by gaining 2 extra electrons rather than losing any of their outer electrons. So chlorine being in group 7, to complete its outer shell, it just needs 1 more electron, gains that negative electron, becomes -1. For all of the elements in group 6, so oxygen, sulfur, selenium, they are 2 electrons short of a full shell because they've got 6 electrons in their outer shell for all of those group 6 elements. They need to have 8. That's a full shell for them. So they need to gain those 2 extra electrons from reacting with a metal. So the reason why these elements are going to become ions is because they are going to react with other elements, with metal elements, the metal elements reacting with the non-metal elements, and they are transferring electrons. Any chemical reaction that you ever see is where something's happening with the electrons. Okay, in ionic bonds, they're gaining or losing electrons, transferring them. In covalent bonds, they're cooperating, they're sharing electrons. In metallic bonds, they are creating a sea of delocalized electrons. So we will, as I said, go over those other 2 types of bonds in further lessons, but it's really important you understand ions and ionic bonds first before we get onto those. So here's your cheat sheet. I've gone over that for probably too long, but it's a brilliant sheet. I love it. Yeah, because in a moment you are going to be asked some multiple choice questions, and you probably will have to use those the cheat sheet here. This idea. So this idea of the ions relating to their groups. Okay, so the question before you went to off onto half term, and I hope you had a lovely time off, was this one here, this 4-mark question review. We're asking you to explain how oxygen and magnesium will bond to form the ionic compound magnesium oxide. Again, you might notice that oxygen becomes oxide, so does chlorine becoming chloride, iodine becoming iodide. All of the non-metals will, when they form an ion, they will become an ide. Okay, so you have fluoride, chloride, iodide, bromide, oxide, sulfide. They all become an ide when they are forming this ionic bond. Okay, so here's a model answer for you. So what we need to be focusing on here in this question, in any question that asks you about ionic compounds and them forming, you need to be using these keywords, okay? So on this one here, this is written as a lovely answer saying magnesium is a metal in group 2 of the periodic table. Brilliant. It needs to lose 2 electrons. Good. The key word there is lose, okay? It is obviously important that you identify that magnesium being in group 2 is going to need to get rid of 2 electrons, okay? So lose 2 is the key phrase that you need to be using there. Oxygen is in group 6 of the periodic table. It needs to gain 2 electrons. Okay, so this is the key phrase that you need to use to get the marks about oxygen, that one forming an ion. Right? So we've actually already got ourselves 3 marks because we mentioned electrons and we've mentioned that they have been lost for magnesium and gained for oxygen. Okay, and the final mark is going to be coming from identifying that these have formed these ions. Okay, and they have opposite charges. It's very lucky with oxygen and magnesium because they both form either a 2+ ion for magnesium or a 2- ion for oxygen. So it's very convenient for those two because one magnesium will balance one oxygen. Okay, because it's a +2 and a -2, they balance. Okay, it gets a little bit trickier if you have a +2 ion and then a -1 ion. Okay, because obviously in order to balance that one, you'd need to have one of your +2 ion, one magnesium, and then 2 versions or 2 sets of your -1 ion. Okay, so you could have 2 chlorine ions for one magnesium, right? But we will talk about that later. So there's where you get your 4 marks from. You get your 2 of the marks from talking about lost or gained, and you need to explain that that is of electrons. Okay, because if you talk about loss and gain of protons, you're completely wrong. Okay, protons rarely are ever lost or gained from a nucleus. Okay, they're like the core, the identification of that atom. And then the final mark is coming from them being opposite charged, so they are attracted together by electrostatic forces, like I was talking about before. Okay, nice. So if you have any questions about that, please do pass them on. But hopefully you can see where the marks are coming from when you're talking about ionic compounds forming. You need to be talking about loss and gain of electrons, and then them being held together by electrostatic forces, so they're oppositely charged. Right. Okay, so this is going to be one of our multiple choice questions that's going to come up for you. But I am going to give you some multiple choice questions just based on this stuff that we've kind of done already. And so, un momento. Okay, not poll 1, go for poll 3. Right, launching the poll. You guys should have just seen these 3 pictures that I posted onto the slides as well. So just click back.
Yep, they're up there, sir.
Okay, cool. Nice. Those ones. Lovely. So I'm going to leave that for a minute and let you guys work through some of those multiple choice questions. See how you get on. Nice. Cool. Someone's already rocketed through them. Really good stuff there. Hello to everyone who I haven't said hello to yet. Nice to see you all. Good, getting a few more answers in here. I know that some of you haven't started yet. Come on, give it a go. Give it a go. Come on, give it a go. That's what we're here for. Might as well. Yeah, that's better. Brilliant. Cool. Yeah, get some good answers here, guys. Just keep going. Some of you don't get the option to do these, but I can read a few of them out for you later when we go through the answers. Lovely. I'm going to give you just another 2 minutes to get a few more of your answers in here, and then I can talk about those. Oh, brilliant. Like more than half of you have answered now. That's brilliant. Keep going, guys. Very pleased. I said it's great to see you coming and viewing the webinars and things, but getting involved and trying to answer a few questions not only helps yourself to identify what you don't understand, but it also helps us teachers to figure out where the gaps are in your knowledge, and then we can, plug the gaps. Help you to do so, more like. Okay, lovely stuff. Thank you so much to everyone who got involved with the polls there and has given us a bit of feedback. So I'm going to end the polling now. Brilliant. Okay, so first question, define an ion. So small molecule, a charged atom, a subatomic particle, or a particle. The majority of you went for a charged particle, and that is the correct answer. Very good. That's the one I was going for. They are obviously small molecules, but that's not close enough as a definition, because an atom is also a small molecule, but the difference between an atom and an ion is that the ion is charged. Okay, the ion is a charged atom. Brilliant. Subatomic particles are obviously things like your protons, neutrons, and electrons. They are not an ion, but they influence whether or not something is an atom or an ion. Right, question 2. Which phrase can be used to describe the formation of a positive ion? The atom has lost electrons. Very good. This is a tricky concept for a lot of people, guys. So it becomes positive. An atom becomes positive when it loses negative electrons. Okay, there's not the easiest way of
So you're cutting out a bit there. You're freezing a little bit.
In yourself and your feeling. So if you have had a pretty bad thing, it might feel a little.
Sir, we can't hear you very well.
Okay, is he better? Hello?
You're cutting out a bit.
Hello, can you hear me again?
Yeah. You're a bit crackly.
Okay. Yeah.
Still a bit crackly. And you've frozen.
Yeah. It says my CPU.
I don't try turning off the camera, maybe?
Yeah.
I don't know if that will make any difference.
Yeah. Okay, hold on. Quick type in here.
No, it's still a bit crackly.
Yeah, good. Is that any better? Is that all
We
right?
can just talk for a bit and we'll see if we can hear you.
Yeah, it's saying because my computer's got high CPU usage. Yeah, okay. Yeah. I'll keep on going for a second
We can
and
hear you now.
see how I get on. Is that any better at all? Okay, brilliant. Yeah. I think it was because, as I said, I think as you said, the camera being on, my computer came up saying high CPU usage. So something was going wrong with the computer, I think, rather than anything else. Is that a bit better now, though?
Yeah, that's fine. We can hear you now.
Perfect. Lovely stuff. Okay. So I was talking about the polls that we had before. I'm going to quickly get those up, see if I can talk them through again quickly. So we were going over ionic compounds, how to calculate the charge of an ion as well. And I was talking about how the formation of positive ions often confuses students, because you often think because it's gained electrons, because a metal has lost electrons, you would assume that it might become negative. So you sort of get this idea in your head that if something loses something, it goes into negative numbers. Or if something gains something, it goes into positive numbers. Now, that is obviously true if you're using a number line in maths and you're going up and down. But ions are formed because of an imbalance of protons and electrons. So you have to remember that. You have to remember that if an atom loses something negative, then it's got more positive stuff. So it's going to be positive. And that's what happens with metal ions. So they form positive ions because they've lost negative electrons, right? So they've lost this negative stuff. So now overall, they've got more of a positive charge. And it's the opposite for these negative ions. So negative ions for non-metals, they all form negative ions because they gain negative electrons. Okay, so you have to remember that electrons are negative, and when they are gained by an atom, it becomes more negative. If they are lost by an atom, they become more positive. Okay, right. So using the periodic table to find out the following charges of sodium. Sodium is a positive 1 ion because it's lost 1 electron. For question 5, which charge would an ion of an ion would chlorine form? That would be a negative 1. The majority of us got that correct as well. Really pleased with your answers here, guys. What charge of an ion would oxygen form? That would be negative 2 because it's in group 6. So oxygen needs 2 electrons, 2 negative electrons to complete its outer shell. If it gains 2 negatives, it becomes 2 negative, okay, or minus 2 in terms of an ion. All right, number 7, what charge of an ion would magnesium form? So magnesium being in group 2 is going to form a positive 2 ion. Right, last question then. Look at the 3 diagrams on the slideshow. Which of these 3 diagrams best shows an ionic structure, e.g. sodium chloride? Right, so I knew this one might be a little bit of a tricky one for you. Okay, so you are quite correct in that C on these multiple choice questions shows sodium ions and chlorine ions that are bonding to it. It does show that these 2 ions, okay? This is the electron shell diagrams for sodium chloride. That's great. That's what a sodium chloride molecule might look like on its own. However, when we draw a structure of an ionic lattice, which is like a little grain of salt, that would actually be shown as A. So out of these 3, A, B, or C, A is the structure of an ionic compound showing an ionic lattice. So A is the answer to that last question there in the polls, because it is showing us the ionic lattice structure of sodium chloride, table salt. Okay, so if we looked at a little grain of salt, it's probably got a little bit more of a similar shape to A than it would to C, because C is just sort of a conceptual thing, talking about the number of electrons in sodium and chlorine atoms or ions now that they've got a charge. So we're going to be talking about this a little bit further now. And if we take a look at this slide here, so ionic compounds on here, there's a few things you need to know about ionic compounds as a general rule. So when we talk about groups of things and we say talk about what characteristics they've got, we might call those properties. And in the case of ionic compounds, they have got a few properties that we need to know. They apply to all of these ionic compounds, or most anyway. So if we have lots of sodium ions and chlorine ions that are all sitting next to each other with these electrostatic forces or charges pulling them together, they end up forming an ionic lattice, like this structure that you've got in front of you. So you can see that the positive ions, the cations, are sort of snugly nestled inside the negative ions, which are, housing around the outside there as well. So they form this ordered structure, one negative, one positive, one negative, one positive, okay, because they have this 1-for-1 charge as well. There's one sodium ion needed for every one chlorine ion. So they form this ordered structure that we can call a lattice, okay? And these ions are held together by these strong electrostatic forces. That's the force of one of them being positive, one of them being negative. Positives and negatives attract. That's an electrostatic force pulling them together. And that requires a lot of energy to break those bonds. They're quite strongly bonded together. So because of these strong electrostatic forces between them, it gives them certain properties. Okay. So they form these lattices, as I was saying before, due to the fact that there's 1-for-1, one chloride ion for every one sodium ion in this structure. So they form this large lattice-like structure, but we don't just display them in this ball format. We can also display them as a stick and ball format, which is this one in the middle. There are obviously pluses of some of the structures and negatives of some of the structures. So there's some good things and bad things about each of the ways that we can display the ionic bonds. Now, if we take the word lattice, a lattice is actually just an interlocking structure like this one. So these crisps are known as lattice structured crisps or lattice crisps because of the way that they overlap with their layers. In this fence as well, this is a lattice structure of the fence. But really, what it's trying to say is that it has this ordered structure, just like the ionic compound lattice that we can see and we've been talking about already. Now, as I've written in here, there's a proper definition is a regular repeated three-dimensional arrangement of atoms, ions or molecules in a structure. So that's the scientific definition of a lattice. But generally, you're not going to be asked to actually define a lattice. You're just going to be asked to identify an ionic lattice. So out of all of these pictures, for example, they might say to you, which of these has an ionic lattice? And you would say, okay, well, the top three are displaying ionic lattices. And then you'd get the marks for those. So just to make a point, it's not a lattice. Okay, just to clarify, not a lattice, a lattice. Okay, ordered structure, not a lattice. So what are these properties? What are these properties that we're going to be talking about as well in terms of ionic structures? What properties do these ionic structures have, and how do they have those properties? So I've written a few along the left here, and I've given you a bit of the sort of keywords to go along with those. So we're going to be talking about each of these as we go through as well. Conducting electricity when molten or dissolved, high melting and boiling points. These are all ionic structure properties. Mostly soluble in water, dull in color, meaning that they're not shiny, and brittle. So in terms of language, we need to understand what the word aqueous means. So you may have seen in some of your chemical reactions that you have the states of matter with L for liquid, G for gas, S for solid. And then there's also an AQ that you can have, as it's written here in brackets, AQ. That just means it's dissolved. Okay, so if you have a substance which is AQ in your chemical reaction, that just means it's aqueous or dissolved in the solution. We also have the keyword conductive, meaning it carries an electrical charge, and soluble is the last one, which means it can dissolve in a solution. Right, so let's have a quick look at this short video about conducting electricity when molten or dissolved. So when it says molten, it just means it's melted, okay?
So we're not getting any sound on that.
Okay, sorry, I need to go and share my audio, I think. Something like that. I just forgot to do that. I thought I knew how to do it. Maybe I don't. Oh, maybe it's on here. It's on the share setting instead. Sorry, Miss, you're gonna have to bear with me for a second again.
That's what I'm just thinking. I normally I just play it and it you can hear
works.
it.
Yeah.
I don't know.
Okay.
Is it?
I'm gonna go for like.
They hear it through my.
No, I don't think so. I don't think so. So you can't hear it now, right? It's not.
No.
Yeah. What I'm going to do is I'm just going to talk over it for the time being, because it's pretty simple what he's trying to show us. Basically, what this chap is talking about is we are going to see whether or not, first of all, water can conduct electricity, because a lot of people get this idea in their head, which is a fair assumption, that water can carry an electrical charge, therefore it's conductive, right? Now, that is true of any of your household waters and any of those other types of waters that you might have at home, okay? So don't go assuming that water can't conduct electricity, because it can. Now, the only reason why water, household water, can conduct electricity is because it actually has some ions in it. Now, we learned earlier about ions being free to move. If they are free to move, they're dissolved or molten. So if they're melted, they're like a liquid form, or if they're dissolved, they're also, free to move around in the liquid. Then they can carry an electrical charge. So they're conductive. Ionic compounds are conductive when they're molten or dissolved, okay? Now, pure water doesn't have any ions in it. It's just got H2O. So these covalently bonded molecules that float around, and they don't have any loose ions, pure water. So they can't conduct electricity. And this chap is just going to prove this point. As you see, he's got a bulb that he's put into this beaker of water. He's got his plug socket there, and obviously you plug the, put the first the electrodes into the liquid. So these two metal rods, which are sort of hovering above at the moment, he's going to plug those into the water. I'm just going to do this now, move it forward. And then turn on the electrical power, which I think he's just done. Yeah, and we can't see, so he's actually already done that. Yeah. So we can't see the bulb. Sorry. Water, can't see the bulb on, right? No bulb on, but he's pouring some salt in now. Oh, and we can see the bulb is lit. So now in this solution, we have got ions. We've got some ions which are able to carry the charge. And the reason why we've got ions now is because we've added sodium chloride or table salt. So in this solution now, we should see some sodium ions and some chlorine ions, which are able to carry a charge. And so therefore we see the bulb light up. So I'm just going to show you this one last time. So we've got pure water here in the beaker. You see the two metal electrodes already touching the water. So the bulb's not on, so there's no current, no flowing. But as soon as he adds more water, see the bulb starts to light up. Brilliant. Okay, so that is proof, or a form of proof, that ions or ionic compounds can conduct electricity when they are dissolved. Okay, now if we were to heat up some salt, melt it, first of all, that would take a lot of energy. Okay, it's a lot of energy to heat up salt to its melting point. It's thousands of degrees Celsius. You'd need probably a Bunsen burner or something like that, as he says in the video, to melt salt. Whereas if you tried to do it at home on a frying pan or something, you wouldn't be able to reach high enough temperatures. But if we were to do that, if we were to melt it in the lab, then we could also conduct electricity with a bulb, just like he's done there, and substitute the water and salt for molten salt, and it should conduct electricity still. So next point that we're going to talk about is this one here. I'm just going to quickly present it so that you guys get the table without the boxes on them first. Now, so this next bit is high melting and boiling points. Okay, and this again relates to the electrostatic forces. So because it's made of positive ions and negative ions, the electrostatic forces are very strong. They're very, very strongly bonded, attracted to each other. And they require a lot of energy to break those bonds. Now, that's basically what turning something into a liquid or a gas is. You're basically breaking down some of the bonds between the molecules, and you're allowing them to flow. Okay, they have enough energy in order to flow over each other. rather than staying in their bonds. So as you can see here, I've got a table with a variety of different molecules. Now, the first few on here are covalently bonded. Ethanol is just non-metals. We've got carbon, hydrogen, oxygen in that molecule. That's a covalently bonded molecule. And you can see its melting point is actually minus 114. So it's going to be, its boiling point is plus 78 degrees Celsius. So it's actually a liquid at room temperature. We can tell that because room temperature is 20 degrees Celsius, and that's in between the melting and the boiling point. So it's already melted. It's a liquid, but it's not boiled, so it's not a gas. Okay. And we can do the same process for ammonia, but as you can see on here, ammonia's boiling point is minus 33 degrees Celsius. So that means it boils at minus 32 or 33 degrees Celsius. And anything higher than that means it would be a gas at those temperatures. So room temperature is 20 degrees Celsius, roughly 22. It's going to be a gas. So ethanol's liquid, ammonia's gas. Right. Now, the actual exercise of what I wanted to do here was I wanted you to be thinking about which of these, first of all, are ionic compounds. Okay. So that's where it's between a metal and a non-metal. So which of these are ionic compounds, and what can we see about their melting and boiling points for ionic compounds compared to some of the covalent compounds that we've got on there? Just going to leave that as a sort of open question just for 30 seconds to a minute, and then we're going to move it on, talking about the work that you guys are going to have set. So another 30 seconds or so talking about which of these molecules, which of these compounds are ionic compounds. So that means they're between a metal and a non-metal.
So I want you to identify which, sorry, if you could repeat it, so a couple of kids didn't hear, just repeating what you want them to do.
Yeah, that's great. So it's just a very short exercise. I wouldn't worry about it now, actually, because we are going to move on. I've actually just given you the answers there. Brilliant. So what I was asking you to do was to identify out of these compounds in this table, which of them were which of them were ionic compounds and which of them weren't. So I've actually drawn red boxes around the ionic compounds that we can see in this table. And the reason I know those are ionic, I've written around hydrogen chloride. That's not an ionic compound. So I'm just going to quickly edit that. The ionic compounds are the metals and the non-metals. So as you can see here, we've got cesium bromide. Cesium is a group 1 metal. Bromide is a group 7. That's an ionic compound. Brilliant. Magnesium oxide, it's metal. Magnesium, oxygen, non-metal. That's an ionic compound. Okay, so I've drawn boxes, red boxes around all of the ionic compounds. And what you can see about their melting and boiling points compared to the small covalent compounds is they're much, much higher. Okay, as it shows from what we were talking about earlier, they have a high melting and boiling points, and that's because of their strong electrostatic forces. So they're really strongly bonded to each other. Right. Most ionic compounds dissolve in water. Okay. So basically, if something dissolved in water, we say that it is soluble. Okay. That's the language that we'd use to describe dissolvable things. We'd say they are soluble. And if they dissolve with other substances, so if they're dissolving in a solvent, we'd call that a solution. Okay, there are thousands of solutions, hundreds of which you will use every single day, and they are, really useful for a variety of different reasons. But you will learn more about solutions in later years. So the reason they dissolve is because the lattice structure is broken up by the water molecules. And you can see this in this diagram here. Here's my diagram before that I showed you of the sodium chloride crystal. So that's like the same thing as like a grain. Well, actually, it's a very, very small part of a grain of salt, what we're seeing here. So we can see that it's got this ordered structure still with the positives and negatives right next to each other in a lattice structure. We need to use that word lattice structure to describe this ordered structure here. Now, if that's put in some water, the water molecules are these little red negatives and the silver positives. That's a water molecule because the oxygen is the red bit and the hydrogens, the H2, are the little positives, right? So now we've put this salt crystal into some water and it's dissolved out, and that means that it is soluble, right? And now the ions, the negative and the positive ions, are free to move, so they can carry an electrical charge. So that's why ionic compounds can conduct electricity in there as well. Right. There are a few ways of representing these structures. So what I want you guys to be thinking about is perhaps why some of these are good and why they're not so good. So this is one of your student tasks for the week. I want you just to write a sort of short description saying which one of these do you think best shows an ionic compound and why you think it might show the best compound. Now, this is actually a really important skill for science, being able to analyze a model and to identify what's good about it and perhaps what could be improved about it. There is always going to be things that you think might be able to be improved about it. One thing I do say that a lot of students get stuck on is you perhaps try and think of something new, a new reason as to why you don't like the 2D version, for example. Okay, you don't have to think of a new reason. You can use any of the reasons that we use in class and which we talk about in terms of why perhaps the 3D model might be slightly better than the 2D model. Okay, so use your knowledge, yeah, and try and state as clearly as you can which of those you think is best and why. The most important bit is why, really. So say why you think one of them is better. Right. So there's obviously lots of different types of ionic structures and they form in a variety of different ways. So I want you guys to try and write what you think the names would be for these structures. Okay, so what elements are in potassium oxide and what elements are in lithium fluoride? What would the name be for magnesium and fluorine being added to each other? So you need to fill that slide out. This next one is about properties again. This is so a lot of the work that you'll get about properties is going to be about analyzing data. So you're going to be looking or perhaps suggesting better uses of certain substances. So in this case, we've got a table of information and you're going to identify which compounds are ionic compounds. And you might want to use some of the properties like the melting points, boiling points. Can they carry an electrical charge to help you identify which are ionic compounds? Then you're going to state the compounds B and C at room temperature. So what state are they going to be in at room temperature, which is 20 degrees Celsius, 22. Will B and C dissolve in water? Yeah, okay. So these questions you're all going to answer on one slide after in order to give your answers there. Right. So which ionic compound do you think is held together by the strongest electrostatic forces? Again, based out on the information you've got in the table. Right. Last little bit. This is talking about empirical formula. Now, that word itself, empirical, often worries a lot of students. Do not be worried. This is really simple. So the way you have to work out empirical formula is by first looking at what charge of an ion it will form, and therefore how many ions will need to balance the other's charges. This makes more sense if I show you this format. So steps of working out the empirical formula of an ionic compound. As you can see in here, we've got a picture in the left-hand column, and the elements that are present are calcium and iodine. And, you know, I could have collected that from the list of elements I had earlier. I'm not going to. Then what we need to do is identify which group those elements are in. So calcium is in group 2, and iodine is not group 1. So sorry, I need to change that over. Iodine is in group 7. Okay. Now that does mean it will form a -1 ion. Okay, so that bit's good. That bit's all right. And for the calcium being in group 2, that is going to form a +2 ion. It's lost its 2 outer electrons, meaning it's positive now. Iodine has gained 1 electron. Now, that begs the question, if calcium's given away 2 electrons and iodine's only picked up 1, they're imbalanced. Okay, I've got one extra electron floating around. I need to change all of these slides. I've got one extra electron floating around from the calcium that's not been picked up by anything yet. So obviously, if I've got loads of iodines in a reaction mixture, and I mix that with calcium, the two electrons, one electron is obviously going to one iodine, but then the other electron is just going to go to another iodine. Okay, so you end up having this overall formula, which is like this, CaI2. Okay, so that's because calcium has lost two electrons, and the iodine can only gain one electron each. So there has to be two iodines present to like mop up all of those other electrons that are going to be left on over there. Right, so I've actually given you the same format to help you guys work through. Oh, maybe it's not on this one. Giving you a similar format to work your way through. And there are also some final exam questions for you guys to be working through in this week's work as well. So the work, when it's posted onto your Google Classrooms, you're expected to complete these last final steps. I'm just going to quickly, because I'm aware of the fact that I closed a load of tabs because I was trying to get my CPU to start bearing with us a little bit better, and I've not opened the right copy. So just give me 1 second. If you've got any questions, can you please put those into the Q&A box now for us, and I can hopefully try and answer some of those for you on the spot. Otherwise, we're pretty much at the end, and it's nearly time for you guys to head off. Just trying to get this last little bit to show you.
I'll give those achievement points to those students as well who performed really well too.
That's great. Thank you, Miss.
So you keep engaged, young people, and we're rewarding
you. Yeah, absolutely. So I think I'm just gonna just leave it at that point. The main point, guys, is that you go and check for the end of your slides with these bits up the top that say student task. You're expected to be completing those sections. So and the exam questions are also there to give you the opportunity to have a go at some of these exam style questions. So working your way through the student tasks for this week and doing the Google form that is expected from you this week. But otherwise, fantastic. Keep up the work. As Miss was saying, you're doing a great job. And it's lovely to see so many of your faces this morning. I'm looking forward to seeing as many, if not more, on the next Monday. Thank you, guys. Is there any questions in the Q&A box there at all, Miss? No.
Asking if they have to do the exam questions. The exam questions this week, you do have to do, there's not a huge amount of marks to them, but their mark scheme is also there. So you just do them, write your answer and upload so that your teacher can have a look and see how well you performed. And then we can see what we need to focus on in next week's webinar as well. So it's really helpful. And you can see as well because you're self-marking.
Thank you. Yeah, that sounds great. Cool. So any more questions, guys, email myself or your teachers in order to try and figure out what it is that we can help you with. Keep it up there, guys. See you next week.